And now let's come to the third one. The topic is tribotechnical diagnostics of an internal combustion engine by Professor Phiri.
Good morning. My name is Phiri Ivanov from Peter the Great St. Petersburg Polytechnic University. The title of my presentation is Tribotechnical Diagnostic of an Internal Combustion Engine according to the condition of the oil. Diagnosing internal combustion engines for oil has several advantages. For example, it's not necessary to take the machine out of operation. It's not necessary to disassemble the engine. Engine malfunction can be detected at an early stage, and the catastrophic consequences of the destruction of engine parts and expensive repairs can be prevented. The problems that caused us to do this work are there is no standard time for changing the oil in an internal combustion engine. The modern design of an automotive engine internal combustion engine requires more precise monitoring of the technical conditions. The scope of the work can be used in various branches of mechanical engineering, in power units of ship quarry, railway equipment for commercial vehicles, in cars, and etc. This study was done because of the following reasons. Sorry, I've already told you the reasons. And the object of study was fully synthetic Castro Edge 0W40 Classic A3, Class A3 B4 engine oil. The aim was to determine the cost-effective period for replacing engine oil in an internal combustion engine. The following steps were to be taken to achieve our aim. Fill the engine with engine oil, then I took the oil sample. Ensure that the vehicle's mileage before changing the oil is greater than the mileage stated in the technical documentation. Take the sample of the engine oil after usage, replace it with clean engine oil. Determine the parameters of engine oil before and after usage in the engine. Kinematic viscosity, ash content, flash point, alkaline number, presence of mechanical impurities. Then perform a droplet chromatogram of the engine oil before and after operation in the engine. Then later, I analyzed the results. We analyzed the results. A VAZ 2111 engine installed on a VAZ 2115 car was used. The car covered a 12,000 kilometer mileage and was operated in city conditions. The picture here shows the engine in the engine compartment, the clean oil, and the oil after usage. The first graph shows the oil service life for frequent and rare changes. From 10,000 to 15,000 kilometers, we see that oil service life drastically reduces. The service life of the oil can be increased by customizing the design of the engine, that is by application of cylinder coatings, the usage of low pistons to facilitate CPG, high probability of jamming of the piston in the cylinder when self-installation is not possible. The other method to increase the service life of an engine is by operational ways, that is by ultimate replacement of the engine oil, and second, by engine operation in non-stationary modes due to low quality fuel. This slide illustrates defects in an internal combustion engine, in particular, wear of the rings and pistons leave wear. This can be worse when we are not changing oil during the stipulated period of time, the needed period of time. Test for friction and wear of engine parts is done on the 4-bore friction machine. The object in this part of study are 4 bores, diameter 12.7 millimeters. Bores pass the input control in the amount of 100% for compliance with the technical conditions according to the GOST 8722-2014. According to the results of hardness measurements, bores with hardness from 65.8 to 67.0 units on the HRC scale were selected. With visual inspection, bores were exploded from the batch, on the surface of which were cracks, corrosion, grinding, and bends. The results are seen using an inverted metalographic microscope IM7200 and the calibration glass. To create a droplet chromatogram, the blue ribbon ash disk filter paper was used. Filter paper was placed on a flat non-absorbent base and ore was dripped from a height of about 5 centimeters. Then the paper with a drop of ore was dried under natural conditions for 24 hours. The diagrams here show the dimension characteristic areas of a droplet chromatogram. It's got the core, where heavy metals settle, and then it's got the marginal zone, and then the diffusion zone for ores, light dissolved organic impurities. After calculating the DP, that is the coefficient of detergent dispersing properties, and the MI, that is the coefficient of mechanical impurities, the graph of the DP and MI in relation to mileage was plotted. For used ore, the coefficient of detergent dispersing properties and the coefficient of mechanical impurities were 0.352 and 0.7 respectively. Where the two lines meet is the critical value of the service type. So as seen on the graph, our critical value is around is in between 8 to 12,000 mileage kilometer. The diagram shows results of friction tests of clean and used fully synthetic engine ore in a 4-bore friction machine. After processing the results, it was found that clean and used ore had the same amount of holding loads, PW, critical load, PC, and Tesa index, Q. Perhaps this is due to the load discreteness of the establishment of number of loads, which is due to the design of the friction machine itself. However, a clear distinction is observed in the wear rates, W, which characterizes the anti-wear properties of the oil. This indicates the decrease in the anti-wear ability of the oil during its operation in the engine. As seen on the graph, the viscosity and the wear rate of the ore increases with increase in mileage. This is due to the accumulation of wear products in the oil, as well as the products of combustion of ore and fuel. This affects the service life of the engine. The wear rate of the samples during friction in pure ore was 6.15 times 10 to the power negative 6 millimeters per meter, and during friction in the used ore, it increased to 2.39 times 10 to the power negative 5 millimeter per meter. The viscosity measurement results showed an increase of more than 30% from 16.3 millimeters squared per second to 23.4 millimeters squared per second. To know the amount of mechanical impurities in the ore, a test was carried out with the use of a filter paper. Before filtering the ore, the mass is less than after filtering in both cases, that is Castro and Motu ore. This is because all decomposition products and wear particles settle on the filter paper after filtering. So we can see that Castro, before filtering, it's 0.698, and then when we filter it, because of the impurities that settle on the filter paper, it increases to 0.729. And for Motu, we can see that it's 0.724, but after filtering, it goes to 0.732. The two tables on this slide shows physical-chemical parameters of pure and used ore respectively. For instance, we can see that the kinematic viscosity of pure ore at 40 degrees Celsius, that's low temperature, is 82.31, but the kinematic viscosity of the same ore but used at 40 degrees Celsius is 76.09. But when we reach a high temperature of 100 degrees Celsius, the kinematic viscosity is 13.52, for pure ore and 15.18 for used ore. Thereby, we can conclude that the kinematic viscosity and the density of the ore increases as we use the ore in our engine. The following conclusions were made. A cost-effective period for replacing engine ore is set in the range of 8,000 to 9,000 kilometers of the vehicle. In a working internal combustion engine, the viscosity of the ore increases due to the accumulation of wear products and combustion products of ore and fuel. Engine ore loses its anti-wear function due to the activation of the additive package, which can cause damage to friction surfaces. With a decrease in the ore service life, engine wear increases and its service life decreases. Thank you for your attention. If you've got any questions, you can ask me now.
Thank you for your presentation. That's a theory, right? So, is there any question? Professor Hong would like to ask you some questions.
Okay, it's a nice job. And may I ask you questions about from your slide maybe 13, you also measure water content. Do you have measured the water content in your oil?
Did they measure what?
Water content.
Water content.
Water.
The water content in the ore wasn't measured. This one was specifically done for impurities as a result of wear and the additives that are caused, like soot. When the ores are reacting in an engine, there's something we call soot that is created that reduces the work life of an engine and it pollutes the ore. So unfortunately for this work, the water content wasn't measured.
I'm sorry. Yeah. Do you have find something relationship between water content and wear scar?
Excuse me, I can't get you properly.
Did you find any relationship between water content and wear scar?
The viscosity and water content.
Wear scar.
Wear scar.
Oh,
Okay.
if you're talking about the relationship of water content and the viscosity reduces with water content in it. But that wasn't mentioned in the presentation.
Okay.
Because it gets diluted when there is water in the oil, right? The oil gets diluted because of the presence of the water. So the viscosity in relation to water content, the viscosity will also reduce.
Okay, thank you.
You're welcome.
Thank you. Is there any question? If there's no any further question, then let's move to the fourth presentation.